All right, thanks. So welcome everybody. We're past the equator, so maybe that encourages us light at the end of the tunnel. So today I want to really focus on our case study, and the idea is to work out what technology, what methods do we need in order to implement some of the strategies we had for Legendrian knots of the form lambda beta. So we're going to consider a Legendrian knot of the form lambda equals lambda beta. And remember that meant in the front, that looked like you take a positive braid beta in some number of strands, and then you close it up with this -1 twist braiding. And for things that are kind of technical, I'm going to have this W knot. For instance, that ensures there is a Lagrangian filling to begin with if beta has Demeter product W. So that's the general statement. And so in here, I'm always thinking of this as a one-dimensional piece of data. So beta is like a linear thing. So I can think of, so for this example, for here, beta is going to be the following braid word, sigma 1, that's going to be drawn in blue, then sigma 2 squared, that's going to be drawn in red, and there's sigma 1 again, sigma 2 squared again, then there's sigma 1 squared, and then there's sigma 1,
2.
Yeah, sigma 2 squared. Right? So what does that mean? Well, as a braid, what you would be seeing are the following. You would have 3 strands like this, and you would first intersect the first 2, then you would have a dip for the next 2, then you would have another one here, then you would have another dip for these 2 guys. That would be 1, 2, 2, 1, 2, 2. Then we'd have a dip between these 2, 2, 2, and then you would have one above here, and well, another one. Yeah. Okay, so that would be the braid word beta that we're representing. And remember, we're doing beta, and then on top of that, we do a half twist at the end. So for 6 strands, you could take 1, 2, 1 to be the word, or 2, 1, 2. The 2 possible words, but that would be fine. Okay, so this is the Legendrian you're studying. For those of you who are thinking about these things, these are max TB, and these are rotation 0. These will fall from the fact that they are admitting horizontal fillings that are embedded. And now the goal is to build a Lagrangian filling. So now I'm going to use several things from each lecture. So from lecture 1, what did we learn? We learned that if we have the front, there's a series of moves we can do in order to go down from that Legendrian via an embedded exact Lagrangian covariism to a knot that we can already fill. For instance, a knot that we can already fill is the knot that's made out of the W knot on the top and the W knot in here. So essentially, you can think of these as we've made it down to the unlink with n components, if n is the number of strands. So in here, the knot that would represent W knot squared, that is the 3-component unlink with 3 max TB knot components. Are we okay with that? Okay, so the name of the game is you start with this braid word, 1, 2, 2, 1, 2, 2, 2, 2, 1, 2, and you have your moves that allow you to go down. And that becomes a very algebraic problem, in particular, like combinatorial algebra people really like. So what's happening here we're having in this piece, to begin with, a d4 minus covariism. So we're using that move from lecture 1, a d4 minus covariism. When can I do that? I can do this d4 minus covariism whenever I see 2 points consecutive to each other, and then essentially these 2 crossings will go down to 1 crossing. Notice that there's a significant difference between 2 strands and the rest. And that also happens in combinatorics and algebra. 2 strands, it's here, trivalent graphs, super well studied, super understood. Every pair of crossings will have that property. In 3 strands, that does not happen. So I could have given you a braid if I would have been a bit nastier. For instance, we'll run an extra 3 up here, and then maybe another one in here, in which there's no consecutive crossings like that. And so, for instance, now if you just looked at this piece in here, you would have 1, 2, 1, 2. I cannot do a d4 minus. And that's why I told you that years ago, I gave this whole lecture on the Rademacher 3, how useful and important it is. So the statement is, nice combinatorial exercise, if you have a W knot in here, you can always have 2 pairs, a couple of crossings next to each other after some braid moves. Okay, so now what are the allowed braid moves? So now go back to your undergrad freshman group theory or whatever you were in the braid group. There's 2 important relations if you take the RD generators. So the RD generators are the ones that take 2 consecutive strands and swap them here. And one of them is called the braid move. which is this thing that says si plus 1 si is the same as si plus 1 si plus 1. Namely, 1 to 1 is the same as 2 1 2. So the way we think about it is, if we have consecutive strands, and the technique that I'm using for drawing these is blue is always S1, red is always S2, and blue is always S1. And I mean, this is in general si plus 1, and si. So whenever you see blue, red, blue, you are allowed to go to red, blue, red, because those are adjacent strands. I'm also using the convention that green is S3. In general, it is a strand that is not adjacent to this permutation. So what would this move be? How do you call this in the break group? If you have S1 and S3, for instance, or sigma 1 and sigma 3, a commutation. They do commute. Generators of the art in commute. The same. I have a crossing here and a crossing here. Well, that's the same as having a crossing here and a crossing here. So from the weave perspective, this is the braid move, the standard braid move. Fun fact, this is in what we call A type for a standard Deakin diagram. The whole weave calculus works for any Lie group. And it's hilarious to do weave calculus in G2 or F4. And I mean, I've written this down. It's a lot of fun, but it's still pictures like that. Okay, so what have we done in here? We have a D4 minus cobordism. We also have a D4 minus cobordism here. And now in here, we start to see the first implementation of our Rademeister's 3 move. So this is an R3 move in here, R3 move. And once you've done this R3 move, you see that this last crossing that was in here actually now is adjacent to one, which is also in the same strand. So now you take this guy and you do a D4 minus in here. And now you keep playing this game again and again and again until you aim at getting down to W naught. Does that make sense? Now, is this an embedded exact Lagrangian cobordism? Yes, because every piece is. So you either did the D4 minus, which locally is an embedded exact Lagrangian cobordism, or you did the Rademeister move, and I don't have enough strands here, but if I had 4 strands, I would be allowed a move that takes blue and green like that, and it separates them. Okay, something like that would be, like, we'll just take like blue strand like that and green strand like that, that would also be all right, because that will be sigma 1, sigma 3 goes to sigma 3, sigma 1, the commutation. Okay, so now I've built in here an embedded exact Lagrangian cobordism. So this entire picture on the left defines for me L1 embedded exact Lagrangian cobordism. And because I can cut the unling, I can say Lagrangian filling. So this is a Lagrangian filling. And what were we thinking about? Well, one thing we were thinking about is, now I also want to build an L compressing system. And then maybe I want to start to mute it. Yeah.
Up at the top, is that beta or is that beta omega naught? The braid you wrote.
This one?
Yeah.
That is beta. So
where do you see omega naught in the picture then?
Yeah. So remember how I kept doing
this? The bottom.
I just don't do it because it's like kind of a waste of time. But yeah, the way to do it. So in my last paper with Nick, the one on spectral networks, I know it looks kind of insane, irregular Riemann-Hilbert. No, just skip directly to like section 7 or 8. Yeah. And then there's something entirely explained that has nothing to do with irregular Riemann-Hilbert that says, actually the filling that fills this with the unlink is you put the W naught in here, and then you let you in the next. Yeah, very good.
Yeah. Would you ever have an occasion to take like a braid generator on the left side of the braid and like move it all the way around the rainbow? Maybe through your half twist.
Okay. So very good point. The answer is yes, and there's a calculus for that. So I'm not emphasizing this yet, but the point is, in here you could say, no, don't do the L compressing system business. I actually am aiming for building infinitely many fillings, as many as I can, in this way. Nevertheless, this is finite data, finite combinatorial data, finite combinatorial things. There's only finitely many people that go from beta to there, okay? I mean, up to like doing certain moves. There's finitely many. So how do you produce infinitely many? So one idea, which is what Danny's saying, is you could do this cyclic rotation of the braid. So you could say, actually, let me move by a Legendre isotropy from lambda beta for this beta to lambda beta where, say, this first sigma 1 has gone to here. And then what you would draw is this guy would now kind of, you would move it through here, you would move it through here, and it would go over there. And if you join the W naught in here and you put the W naught like that, that gives you the other Lagrangian filling. And now the claim is, with the cyclic move, you actually get infinitely many possibilities, and we did prove that indeed they are Hamiltonian non-isotopic. So that cyclic rotation allows you to do that. and it can be done pictorially. Yeah, so these things, you can perfectly think of them as being in the disk. And this is in D2. I usually think them top to bottom because of my algebraic collaborators that cannot understand the disk. But no, I mean, it's just for them, it's a linear process. It's a move. And but then the cyclic rotation is
Is it obvious in that case that cyclic rotation, as you keep doing it, you get a different Hamiltonian? So because is it, do you know if it is a this surgery, like the Butterfield surgery?
Yeah, so it's not one, it's typical many. So remember, so they're very good. So if I have a crossing here and I move it to the top, what was I emphasizing the other day? That every time you pass through something who's at the same level, that is a Polterovich surgery. So you actually know how many and which ones, which is every time you pass somebody on the same level from the top, that is a Lagrangian surgery. Yeah. So, okay, so you have this Lagrangian filling on the left, and then you also have this Lagrangian filling on the right. So there's this L2, again, embedded exactly Lagrangian filling. So let's just write filling in here. And now you find yourself in the following conundrum, which is I drew two different pictures. Are they the same Lagrangian filling or not? So you want to have some kind of calculus, some rules that tells you when two things are the same and when two things are not the same. So this is what maybe I should, I think it's a good name, the fundamental theorem of width calculus, of this diagrammatic calculus. So it says the following. It says the following moves up here give Hamiltonian isotopies. So for instance, if I see a Rademacher 3 followed by a D4 minus on the left, and then followed by a Rademacher 3, that is the same thing of just doing one Rademacher 3 on the left and then one D4 minus on the right. And notice, this is very, very important, that these are all REL boundaries. So the boundary up here is the same as the boundary up here, and the boundary down here, that's the same as the boundary down here. And this is truly a Hamiltonian isotopy of the exact Lagrangian covariism REL boundary, not changing absolutely anything at the moment. So for instance, I could have taken this crossing over here, we call this I call this the push through move, because that move is equivalent to taking this crossing in trivalent and let it go past one hexavalent. So it's equivalent to that one. So that modifies the weave. It does look to the untrained eye like a very different weave, especially if you do that many times, but it's actually Hamiltonian isotopy. So the first thing is these are moves that you can do. Another thing is, as long as you don't do D4 minus covariisms, if you started a braid and you end in another braid, which is obviously going to be the same braid, that'd be braid equivalent. So if you started a braid word and you end up at another braid word, which are equivalent, I need that very clear here. So only using these two, that's a consequence of these, then nothing can happen. So you cannot do anything interesting by just doing Legendran isotopies. For contact topologies, this should be like completely obvious. But for algebraic people, it's like very cool. So we call this move, for example, is you do a Rademacher 3 and you undo a Rademacher 3. And well, actually, I said it should be completely obvious. Maybe, but somebody at some point had to prove that doing a Rademacher 3 and undoing it, it's the same as not doing anything at all, which is what's happening here. Rademacher 3 and undo it is the same as not doing anything at all.
But you said kind of moving a crossing around, right? That is also a Legendre isotopy.
Yes, correct. Yes.
So not all Legendre isotopies are trivial. So that's not.
Yeah. So if you think linearly top to bottom, there's a theorem. So okay, relative to the boundary, this boundary and this boundary, this is the theorem.
Okay.
And relative to these two boundaries, you allow planar isotopies. But the move that takes these and moves around, that's not relative to the boundary. So for now, I'm just focusing on the calculus like rel boundary.
Yeah.
That's true. So you have these kind of moves. Another kind of move would be you take these two strands and you separate them. So that would be a commutation and a commutation, undo them. Okay, so these are moves. This is useful. It's like having Rademacher move, like the easy part of the theorem. These Rademacher moves are isotopies. So these are ways to go from one Lagrangian filling to the same Hamiltonian isotopy class, but a different representative. Okay, statement number 2, and this is something we kind of discussed yesterday. If you have this picture in here, you can think of the lift of this arc that actually is an S1 that bounds a disk, and that disk is actually a Lagrangian disk. The boundary of this Lagrangian disk is the S1 that lives in your Lagrangian filling. Therefore, you can do Lagrangian disk surgery along this D, and you obtain a new one, and that's D prime. And from the picture, it looks exactly like that. So for experts, or if you look at the papers, you're gonna see sometimes that there's a mutation to something that doesn't look like a straight line like that. You're gonna see things like mutation along a tripod, like these two guys in here united in there, and we still mutate that. That's why I added the word locally. You can combine this move with Legendre isotopy. So for instance, you can start with some complicated weave, go down through Legendre isotopies in one until you get a short cycle like that. Then you mutate and then you undo it. And that will produce something that's equivalent to a mutation. So up to conjugacy, this is how it looks locally, but in general, they might look much more complicated. So again, this idea that combining something interesting, a D4 minus cobordism with isotopies is an extremely rich thing to do. It gives you a lot of leverage. And in fact, I mean, my conjecture is gives you all. So, okay, this is useful. This is kind of nice. Okay, the theorem up to here. But now you want the reverse of the Rothe-Meister theorem. And this is the reverse. It's like any two weaves between two words, rel boundary must be related by these two kind of moves. So that tells you that, you know, if you really want to go from a weave like this to a weave like that, it would suffice to only look at those moves, and you can do that. Okay, questions so far on this? But
Two comments. Number one is that black marker you're using is slightly FE right now.
thanks. R3 plus reverse of 3, that's the same as beta 2.
Number two is, do you care that the bottom of these two cobordisms are technically different? There's blue red versus blue red. Or
If I want to be legit, the answer is yes. So let's.
Okay, yeah.
I was running out of time when I was like knowing all of this, and I didn't pay attention. But that's a very let's all be like exactly precise boundary, the same great word, not just an equivalent one. Okay, then or
So,
go ahead.
I was gonna ask, like, what do you mean by like a weave from one braid to another braid?
Oh yeah. Sorry, so maybe I should have defined. So a weave is a diagram that uses locally either a trivalent vertex, which is a D4 minus cobordism, a Rothe-Meister 3, which is an hexavalent vertex, or the commutation move. And the commutation move, so the commutation move is the move that is you have S1, say, and then a non-adjacent S. So any graph embedded in the plane that has these boundary conditions, given this beta and some other beta in here, any graph that goes top to bottom by doing the moves, these, the trivalent the trivalent D4 minus and the hexavalent Rothe-Meister 3, that we call it. Technically, it's called a Demeser weave, which is slightly more general. But when I say weave here, I mean Demeser weave.
Okay, this mostly answers my question. So you don't allow like cups in the statement?
Maybe not. Yeah, not in this lecture.
Okay, what about
Yes, in real life.
what about an upside down
Trivalent?
minus move? Yeah.
For a general weave, yes. For a Demeser weave, no. So a Demeser weave is explicitly this kind of linear thing top to bottom. So in particular, the Demeser weaves do not deal well with cyclic things. But a general weave would just be like anything that locally looks like this in the disk, for instance, or in any surface. And that there's no directionality. So actually it doesn't even make sense to think about like I'm going this way or the other way. So when we first introduced with Eric, it was like just this general thing. And it described fronts of Legendrian surfaces. But when we want to think about Lagrangian cobordisms, you want to make sure they're embedded or unobstructed. And now you need to start like developing tools so as to make sure this is because if I put a cap, for instance, that's a clasp move. So that makes it inverse. You kind of gotta be careful about these things. Okay, very good point. All right, so this is the status. This is kind of the wave calculus for you right now. And now you try to implement sort of the thing that I've been trying to convey, which is to say, okay, one way that you can think about it is I want to build many fillings, maybe in that way. Or alternatively, I want to build one filling, but I want to have an L compressing system in it. Does that make sense? Now, I want to tell you something that's kind of important to remember. Suppose for a second, I tell you how to build an L compressing system here, which I will in like 3 minutes. Is that enough? Well, here's an important example to keep in mind. Take the example of the trefoil. So I didn't have time to draw it there, but take the example of the trefoil that we were doing the other day. Say, take this weave in here. that was filling the trefoil, 1, 2, 3, 4, then 5, that was -1 closure of that. Here, the compressing system was very clear. The first disk would be here, D1, and the second disk would be here, D2. And now you can start doing mutations. Now, when you start doing mutations, you will change the weave in an interesting way. And for instance, you can first mutate at D1. Then it would be silly to mutate again at D1 because you would go back because it's evolutive. So then you mutate at D2. And then you look at that one and maybe you argue by hand, okay, that actually is not the same filling as neither of the first one or the second one. And then you mutate again at D1, actually I've produced a new fourth filling. Then you mutate again at D2, I've produced a new fifth filling. And then you mutate again at D1, and you're like, I've now produced something and I cannot tell it apart from the first one. So what is going on in there? Well, what is going there in that specific example is that actually that fifth filling, the filling obtained by doing 1, 2, 3, 4, 5 Lagrangian surgeries, is actually Hamiltonian isotopic to the first one. There's an interesting relation that's happening in the trefoil. So beyond having an compressing system, which is a useful thing to do, we need something else telling us that those fillings are different when they're different. Because if we just look at the weave itself, even if I give you the compressing system, you know what I mean? Like, suppose I have an compressing system here, mutated with Lagrangian surgery, and suppose you get here with another compressing system. How do I tell them apart? I mean, I'm producing candidates, right? That's step one, I'm producing candidates. Okay, so the short answer is you use sheaves, okay? So you want to now understand the model I of sheaves here and the model I of sheaves there. And what's happening is that both of these, TL1, so you have this L1 in here, and you have this L2 in here, and then both these guys are going to give you in M of beta, they're going to give you two tori, TL1 and then TL2. The goal is to show that these two tori are different. Does that make sense? So you can sort of try to find a point here which is not there, so on and so forth, or you can be like really ambitious. And you can say, actually, I'm going to find equations that cut out these tori, equations I mean inequalities. Inequalities that cut out this tori and inequalities that cut out that tori. Good start, good to go. If a grad student told me, I have this idea, I would say, good, go work it out. And then they're going to come next week probably and say, well, when I have these equations and these equations, sometimes they look very different, but they define the same torus to me. That's what happened, for instance, for the trefoil. After you mutate these 5 times, the equations look kind of different, but then you realize, actually, this inequality follows from these ones, this follows from those ones, and conversely. So actually, the two tori are the same. So then you say, okay, why not? Be childish about it. Let's find canonical equations. So let's not just find equations, but let's find functions, specific set of canonical functions for each torus, such that the torus is defined by the non-vanishing of those functions, and more importantly, such that if these two sets of functions are not the same, then the tori are not the same. Does that make sense? So to me, the great beauty, the big kind of conceptual advantage after I did all this was to realize that there are particularly nice canonical coordinates in here and in here that have this amazing property that just by looking at it as a set, I can tell, well, the two sets are different, the tori are different. Does that make sense? So flash forward to later today and a bit tomorrow. These are called cluster coordinates. There's particular cluster A coordinates. And right now I'm going to try to ease ourselves into what are those coordinates geometrically. Is the plan clear? Okay, so you're doing geometry. You want the functions on your space to be geometric. Now, shortly, you can coordinatize these with the Z1, Z2, Z3s that Konghao is doing, and you can take, now you're in a affine variety. How many functions does an affine variety have? Plenty. Just take any coordinate function and restrict to it, see what happens. Highly non-canonical. If I did some Rademacher moves or I did something like that, it's very unclear which functions you should be choosing. So, don't do things coordinate-wise because you're not going to see really what's happening. So instead you think geometrical. So what do I have? I have a Lagrangian surface in R4, and now you use that it's sheaf quantized. So out of this Lagrangian surface, remember, there exists a sheaf quantization, FL1, but not only that, given by So the fact that there exists a quantization essentially is the same argument as Jim Truman, like Wen Yuan and company, like Wen Yuan this result. So there exists a shift quantization, sure, meaning there's a shift on R3 whose singular support is L1, yes, but given by what I initially called in the first paper, flag model line. In the sense that it's not just an abstract quantization that you don't understand, it's a very explicit quantization. What you're putting here is a flag, in this case, a flag in K3. So a point, a line, a plane in 3 space. And here another one, and here the 2 planes differ. Here another one, these 2 planes differ. Here another one, these 2 lines differ. And now, this locus, TL1, is exactly the locus of flags, tuples of flags on the top that survive the conditions imposed by the trivalence. Now, the hexavalence being isotopies don't give you any extra conditions, which is saying any flags on top, the 4 flags on top on here will propagate to 4 flags on the bottom. Yeah. So now you cut out these people through these kind of lens of the flag, so you don't just have a quantization, a shift quantization, you have an explicit shift quantization through the exothermy description that translates the problem on the shift to a problem of flags. Is that clear? Okay. So now you have this very explicit shift quantization. And furthermore, you have the microlocal functor. Namely, you have that given a shift, you can apply the microlocal functor, and you're going to go where? You're going to go from, so this data gives you which data? Gives you the data of a local system. This is the microlocal functor applied to shift of L. It's going to give you a local system L on, sorry, mathematical L on. Okay. So I don't just have a surface, I have a surface with a local system given by this specific shift quantization. And there's many shift quantizations, and each of them is going to give me a slightly different local system. Does that make sense? Okay. So now things should start to be okay for a geometer, because I have a surface, it has a bunch of curves in it coming from the L compressing system. So say I take one of these things from the L compressing system. For instance, I take this curve in here. So there's some curve gamma I bounding this di, and di is in my L compressing system for Lagrangian L, L1. And now, okay, what do you do if you have a surface with a local system and you have a closed curve in it? Nobody. You often would take monotony, right? So what would you do is you would say you would look at the stock at the local system at a point, follow the curve, say orient it in one way, follow the curve, and then it's going to go back to the same local system. It being a local system, that's going to define an automorphism of the stock. Does that make sense? Local systems on S1 is representations of phi1, which is exactly, CX modules, so a vector space with ZX and Greenberg's modules, so a vector space with an automorphism. Are we okay with this geometric picture? So the first thing you do, or I don't know, one thing that you can think of is you do that. Now, historically, Fock and Goncharov, so Sasha Goncharov and Vladimir Fock, were the ones who connected the theory of local systems, nothing to do with Slavic topology, with cluster stuff. So that's already, if you look at historically, it wasn't me who went like, oh, it's like, I don't know. Fock and Goncharov already were like, local systems have a lot to do with cluster coordinates. So that was already a first hint that this should be very wealthy in results in connections to cluster algebras. So, okay, so you take this monodromy, you're feeling good about yourselves, and you say, let's compute it. So now you do an example. So let me do an example here. Space that much. So let me do an example in here. You take 2 fillings of the half length. So this guy versus this guy. And remember, this is the half length, right? Does that make sense?
There's the same feeling.
Challenge myself, huh? So, thank you. So you have these 2 different fillings of the half length now. They differ by Lagrangian surgery, and you're like, okay, so I have monodromy around gamma, and I have monodromy around gamma prime. You can, for instance, coordinatize in here m beta, and remember how m lambda beta, and remember that we've hooked up this guy a number of times, and it looks like points xy in C2 minus points that satisfy 1 plus xy equals 0. So it's all points xy such that xy plus 1 is not 0. So x is a perfectly fine coordinate in that space, right? And you compute this monodromy, and in actually the monodromy around this one is X. So monodromy around gamma is X. What does that mean? Let's think about it for a second. These moduli, the points are sheaves which give local systems. So X specifies a specific local system. So this is a function, quote unquote, on the space of local systems on the surface, at least for that chart for that filling. And the function, what it does is it takes a local system and it evaluates its monodromy around X. So depending on the point that you are, the monodromy is going to be multiplying by X and X will vary. And so there's a function evaluated in that chart. So there's some C star chart and there's another C star chart. Does that make sense? So now you're really like, this is fantastic. This is going to be Y. Everything's fine. Beautiful. Anyone just wants to guess what the monodromy theory is? X.
Universe.
One over X. Now just look at it for a second and weep. Because like this is extremely dramatic. This is telling you that taking monodromies does not give you functions on your space. Specifically, it does not give you elements of the ring of regular functions because it's not a regular function. Here it might be, in this chart it is, but it acquires a pole in the other chart. X equals 0 is a perfectly fine non-empty set in my variety. So this is a rational function, is an element of the rational field, but it's not an element of your commutative clusters or commutative algebra given by the ring of regular functions, which is the ring that, you know, everywhere in algebra geometry, you kind of initially care about. Like the thing you would take a spec of in order to define this, if this were to be a scheme. Does that make sense? Okay, so I just try to like summarize, I don't know, I think there were about maybe 4 years where we went to realize that this was really bad, figuring out the solution. So now this was bad, we figured out it was bad, and now what do you do about it? So what's nice, and this was first stated in a paper I wrote with my postdoc, then postdoc Dapping Wang, down in North Carolina, UNC, is we realized that the right thing to do geometrically is not to take monodromies around here, but plot twist, you do the following. You take the L compressing system, which is going to give you a bunch of curves in it. For instance, it will give you this curve in here. It will give you this curve in here. I'll tell you how to compute this once. It will give you a bunch of curves in it. Suppose it's maximal. And for these kinds of Legendrians, you can make it maximal. I mean, it's part of the theorem. The theory is that you can make this a maximal compressive system. Then now you have a basis of the first homology of the filling L. What can you do if you have a basis, by the way, that you couldn't do if you just had one curve of, say, H1 of L? You can take the Poincare dual of the basis. If I had one element, it doesn't make sense to talk about the Poincare dual. But if I have an entire basis, I can Poincare dualize it. So I can try to find a basis in the dual of cohomology, which is going to be a relative cohomology here, L relative to the boundary, such that the element, say, eta I, eta being the dual, is such that it pairs exactly with gamma I1 and with all the other gamma J 0. Does that make sense? So now we're back to like kind of undergrad or first year Hatcher stuff. What does the Poincare dual look in this kind of pictures? So if I have a bunch of surfaces spanning the homology, so a bunch of curves spanning the homology of a surface, and there's boundary, what does Poincare dual of that look like? And if you think about it, the things that you're going to get are things that go to the boundary. So for instance, if I don't care immediately about like how to draw just smoothly, the Poincare dual of this, for instance, can be a curve that essentially does this, right? Because that's a curve, eta 1, that pairs exactly intersects 1 with gamma 1, and it won't intersect anybody else either. Another Poincare dual, for instance, will be something like that. So if this is like gamma 2, this would be like a representative eta 2. Does that make sense? And now, does it get complicated? Well, yes, it does. These compressing systems might be kind of elaborate curves, but you are able always to build a non-compressing system together. Yeah. All right. So let me tell you now how to just diagrammatically find the L compressing system, how to diagrammatically find the Poincare dual, And then I'm going to tell you after how you get the functions out of the punctuator. Does that sound like a plan? All right. So the diagrammatics of this are as follows. So given any Demeter weave, so any weave as there are a series of rules that define what we call the Lustig cycles. And the Lustig cycles, though they're defined algebraically, what they're doing is exactly building for you typically an uncompressing system. So for the experts, there's a little asterisk. What I'm going to say is always true if beta itself is W naught. Otherwise, it's a little asterisk in there. But effectively, at least at the first time that you're thinking about this, think that this will produce an uncompressing system for you. So here come the Lustig rules. So the Lustig cycles. So for each trivalent, so that's for each time that you do a D for minus cobordism in weave. So this is W. Say that this is a trivalent vertex, B in W. You build what we call gamma sub B, a cycle that will belong in the first homology of L. How is that cycle built? So the rule is every time that I see a trivalent vertex for each one, this is my little v, the cycle will start by going down. So I should color code this thing. The cycle will be gamma v, and the cycle will always start in here and go down. Now remember the thing from the last lecture yesterday. What this is when you take the branch cover is an arc that looks like two things branching over it except at this point. So that's, if you want to think about it, it's a descending manifold of the saddle point cobordism. Okay. By the way, like don't panic, like you have these the rules like written for at least for the next hour. So if you forget them, forget them. But the rule is this is how it starts. So the rule is here gives the start. And now you have to understand what happens as we go through the weave downstairs. So it propagates down via the following rules. So suppose my cycle, and I'm going to just do an example here. Suppose my cycle is continuing here, and then it meets some other strand in here that has nothing to do. So this is S17, and maybe the blue was like S1. For instance, I mean the colors just mean these are disjoint. If you find something like that, what would your intuition be? So the weave up here is some cycle that you're keeping track of sheets 1 and 2, and something that has to do with sheets like 17 and 18. You completely ignore that. You just go there. No problem. That's fine. So you keep going. But now you find a second kind of interesting interaction, which is it might be that somewhere down the road you were finding a trivalent vertex, sorry, an hexavalent vertex, or Rademacher 3. For my brain, it's so hard because it's Rademacher 3 and it's the hexavalent. So I always sometimes call them trivalent, but it's not Rademacher 3. Anyways, you know Rademacher 3 in here, it's coming like this, and then it continues. Well, you can think about it carefully, but at least when it arrives from the left or from the right, the rule is it just propagates through. Nothing is happening in here. Okay, so far? All right. So now comes interesting stuff. Like suppose that somewhere in there, now you have that this guy, maybe this guy goes and pinches with something else. And now somewhere in here, there's some blue coming. I don't know, to give you an example here. This guy now continues in here and opens up in there. And he continues like that. The interesting move, the thing that really gives juice to the theory, which happens especially when beta doesn't have a W naught a lot, is the case in which you enter an hexavalent like that, and then what you do is exactly you propagate in both branches. So that's that rule that I wrote down here, and that's maybe the most non-intuitive rule of all, because a lot of people would just say, well, just keep going through, and you just kind of keep going through. That doesn't work. That doesn't work in many levels. It doesn't give you regular functions. It doesn't give you cluster structure. The quiver's not right. Everything is wrong. Okay. So now, how does it end? So this is what's happening in the middle. So every time that you hit a trivalent vertex from the right or from the left, so in this case, for instance, hopefully this is a good example, like it illustrates that either coming from the right or from the left, the end will always be at another trivalent vertex. And think about it, over these, there's always 2 points. So what you want is that they go somewhere to the branch point and they join. So this is an example, this is the example that corresponds for this cycle, so for this trivalent vertex, the descending manifold kind of propagates like that, and it produces this closed circle. So this is a circle. Okay, this should be thought of as S1 in the Lagrangian filling L associated to the weave W. Does that make sense? Okay, so those are the rules. I went through the sort of rigorous argument necessary to argue that all of this is well defined. It can be done combinatorially and algorithmically, and I strongly recommend that you spend hours like playing with it if you really want to understand what's going on. I don't recommend that you do the same as I did, because it took me like months and years to figure out the whole thing and where everything matches. But that's the point of progress. Like, you know, I do some of the groundwork and you don't have to do it, and you do some of the other groundwork, so on and so forth. But this is exactly how Lustig cycles propagate from V to something else. Yeah.
So if these are jetsam multifunctions, are these kind of like gradient flow trees with some sort of twist to make them Lagrangian?
The word twist makes a lot of heavy lifting there. The answer is yes, if twist means something appropriate.
Some sort of hypercalar or something.
Yeah, but that means that this needs to be like holomorphic to begin with. But yeah,
Okay.
in that setting, so in my paper with Nick, in the setting in which you started with an holomorphic Lagrangian, or elliptic to Legendrian,
Mhm.
then you have this theta rotation, because you can take the real part of that.
Mhm.
And then depending on the theta, these are the holomorphic trees. So they're in particular the gradient trees, they're the real Morse flow trees. And for another theta, the flow trees are sort of orthogonal to that. And these are kind of the branch cuts that allows you to compute. So depending on this, yeah, in that specific, there's a lot of rich geometry, and you're correct.
Mhm.
So there's a hyperkähler rotation business going on. And this is actually, so this is the thing, like in that specific setting, for some thetas, this is a circle that bounds a Lagrangian disk. And when you vary the theta, that Lagrangian disk becomes an holomorphic disk. That's
Yeah.
the wall crossing business.
Mhm.
Okay, are we content? Are we like satisfied so far on how to build a Lustig cycle like that? Yeah.
It's like, when you're doing this top to bottom.
Yeah.
I can see the difference between these two, 6-strand crossings, but if you were XL, the trivalent loops, sometimes you
Yeah.
go through it, sometimes you branch, right?
If you go from the left or from the right, you go through. If you go from the middle, you branch.
Right, but if you were drawing in a disc, so
Right.
like this top, then it's hard. right?
Well, then there's no definite theorem there yet.
I see.
So, as I said, the theorems that I'm stating today are completely rigorous, written in the literature for them as weaves, and they give the right answer. It is an interesting question in general. Had I had the weaves just like roaming about, how do I produce L compressing systems in there? And in some cases, we do know the answer, and in some cases, we don't. For instance, in the case that the weave is what's called the T-dual of a Plavy graph, that is something I wrote with Sherman Bennett, Ian Lay, don't say Sherman Bennett, Colin Davis, Daphne Wang, and Ian Lay. So in some cases, we understand how to do that too, but in general, yeah, it can be subtle. I mean, in part because it's not even obvious that it's immersed to begin with, not because it's embedded or not. You can compute the topology by Riemann Horowitz, because you know the only characteristic, so that part is easy. But then like how we did that's something else. All right, okay so far? Okay, so given each of these trivalent vertices, this guy, this guy, this guy, you should be able to produce something like that. So let me just be very quick about it. This guy, for instance, will produce this kind of gump. So if this is V1, that will be your guy in here. The second one will be this one here. This one is also very easy. You just do this one. This one is a bit funkier, but because it goes through the trivalent, but then it comes back to itself. And there's, for those of you who care about frozens, these two will be frozens that will do this, and that's okay. And finally, there's this one. So in this particular example, there wasn't any series bifurcation, and everything was kind of this long thing. But in some examples like this one, if I started here, I would have to bifurcate and then end at these two ends. Yeah. So now you take every trivalent And if your cycle does finish somewhere finite, that's what we call the mutable variables, then you have this L compressing system coming from these circles in the Lagrangian that bound Lagrangian disks just by virtue of being built via the width method. Okay, monodromies along them do not work. Monodromies along them give you what's called a cluster X variable, but what they don't tell you is, oh, cluster X variable and A variables are dual. Yeah, but ones are useless and the others are not. It's not as dramatic as that, but the cluster X variables are rational. You cannot really use them as an element of an algebra. The cluster A variables are actually elements of a commutative algebra. So how do we build a cluster A variables, the things that are going to be regular? So before here, I drew something like something that went up like that. I just want to draw it slightly different. It's the same cycle. So instead of thinking of two things going that way, I'm going to draw one thing on the same tree that goes like this. So if this was the vertex, say this was vertex maybe V3.
Can you use a different marker?
Not black,
No, it's
Better
just becoming pink again. Is it just me?
a better black.
Better.
Sorry. Okay. Well, you should kind of think of it as you look like kind of kilometer. Like that. Okay, so locally, what's the Poincare dual of the descending sphere? The ascending sphere. And that's essentially what's happening in here. You can take the ascending sphere to be this one that's living on the same sheet on the left, and then it crosses sheets to the bottom one, and it goes to the other sheet up there. And that intersects, that's something you have to be careful about. I have pages of matrices in computation telling you how to translate these intersections, which are topological intersections, purely in matrices. So you compute some determinants, and that gives you intersections. And then this guy actually intersects this guy once, because it intersects at this point, but that's not an intersection point because they're in different sheets. So that is intersection one, it doesn't intersect anybody else. So that is a good candidate, at least in this example, of the eta the Poincare dual. So here comes the new conceptual definition that's really, really important, is the notion of, I don't have monodromy, so I can go back to itself, but I have a notion of something that you can call it, you can call it a generalized holonomy. I like to call it merodromy. So, with an exodromy, we get variations in that. So in Greek, like when you say meromorphic, holo means whole, holistic, and mero means kind of partial, only partially, right? Because it's only holomorphic in parts of it, in the poles. So instead of monodromy, which means dromos, path, mono, one path, you go around, mero is kind of a partial path in the spirit of relative cycles. And then what you do is the following. When you have a monodromy around a cycle, like this one, you just fix the stock and you go around it, and there's no extra data that you need. Here, what we're going to do is we're going to start with some data here, parallel transport it to some data here, and then compare those two things. All right? So now I'm going to give you a weave example, something with a two weave that explains this hopefully very clearly. And if you were not happy with it, you can complain. That's right. You don't need a suggestion box, you can just shout. Okay. So let's do the example of the following. So let's just locally this example. Maybe okay, let's do this. Now I'm just teasing you, waiting for you to say these are the same one. But they're meant to be the same. All right, so here's what's happening. Here we have this cycle over here. And what I want to tell you about, okay, this cycle over here is this gamma. And the monodromy, which is not what we're looking for, but just so you have a better understanding of what's going on, the monodromy is what? Now think back to yesterday about all the business about the flats. What do we have here? Here you have four lines. Here we have a line L1 in here, a line L2 in here, a line L3 in here, and a line L4. Cyclically consecutive. So actually, if you have four lines and you have this gamma going like that, could anybody, I don't know, have you heard, what do you do with 4 points in P1? What do you do with 4 lines? What is a way to get a function that's canonical enough? Cross ratio. So actually, this geometric thing that's very natural, which is you take the Lagrangian filling, you shift quantize it, you take the microlocal functor, and you compute the monodromy around it. Translated into flux means you have 4 lines, you compute the cross ratio. I don't. Maybe that illustrates there's a very beautiful geometric justification for what this is conceptually, but then you got to be able to compute stuff, and that's very nice to go about it. And now, if I instead wanted to do the dual, so if I wanted to do this, now I'm going to have 2 lines. In this case, the line L1 and the line L2, L3, in here, and then the line L4. And the first thing to realize is, essentially, you cannot do anything. So if you just have 2 lines, in this case, L1 and L3, this is kind of telling you, about L1 and L3. Sorry, John?
I think one should be shifted to 2, 2 to 3.
Oh, yeah, to compare with this? Yes. 4, 1, 3. Thanks. No.
3's on the far right. Yeah. Perfect.
Okay, so what this is saying is something about the L4 region and the L2 region. Now, what do you know about these 2 lines, given the information of the week, given the information of the filling? You know that these 2 lines are different from each other. So you know that L2 is different from L4. So what do you have here? You have something that's not a function, it's just something that's non-zero. Now, the idea, and that's the key idea in the paper with Dapping, is that there is another modelized space, which is not exactly M beta, but it's something we call the decorated moduli, maybe I should say lambda, which is you can add base points to the Legendre. Let's call this base point set T. And now what can you do with information of the base points? And for people VGA related, you know that is a natural thing to do. If you have base points, what you can ask is a trivialization of the microstock exactly at those base points. The correct way to say it is that you're trivializing the local system away from those points, but you can take a set of points complementary to your set of base points and then trivialize those microstocks, so equivalent data. And that guy is better behaved than that. And again, this is a completely general theme in math. If you have a space that is of the form X modulo some group, if you don't want to deal with kind of stacky parts or really complicated things because the action is not free, you can add subdata such that it forces the group to act freely or at least more free than before. Does that make sense? This is an idea, this is 100 years old. And here what's happening, so you have a good sense of this, is in the isomorphism yesterday, this was X mod T, or generally it was like the space of all flux mod G, which you can like maybe go down to here. This guy is actually isomorphic to X times BGL1. So effectively think of this as an affine variety. So this is a affine variety. So effectively you can think of this that adding these base points and additional framing and trivializations are unstacking this thing for you. And they're producing an actual affine variety where there's no group acting on it. There is a group, GL1 acting trivially, and that has to be there because it's the modifier that you have. Are we okay so far? Okay, so now this is going to be as close to an affine variety as possible. Okay, except for these factors. So this will be a smooth affine variety. And now you want to understand at the level of flux, again, this translation, conceptually, you have this local system, this trivialization of the local system. And now you want to understand what does that translate in the level of flux? What does it buy me from the language of the exotropy description to have these microstocks being trivialized in a common way? Then maybe you can guess the answer. What would it be to frame a line? It will be to choose a vector generating it. So that's exactly the data that you gain if you frame appropriately. It's now you no longer have lines, you have lines with a choice of generator for those lines. What does this buy you? It buys you the difference between a quantity that's not zero, and that's all you know about it, and an actual function. So in a way, you can think that before framing, all this parallel transfer knew was that L2 was different from L4. That's all it knew. Now it knows a measure of how different they are, right? I mean, you can have two lines being different, but you can think of sort of the angle between them. I don't know how you want to think about this. It really is the area of the parallelogram they span. And then that is a quantitative measure. So that upgrades the just being different thing to the fact that now you can compute this quantity. So in here, you can compute the quantity V2 wedge. I'm trying to be intrinsic about this. So you take the exterior power and now you divide by the determinant, like the volume form. And that is a function. That is, if you wrote V2 in this column, V2 in here and V4 in here, that's just like the usual determinant. You don't tell your student that really what's happening is, you get a top form and you're killing like a volume form and you're taking the coefficient, but that is what the determinant is. So you get an actual number for every local system. So that really is a number in K. And actually, because it's non-zero, it's a number in K. And remember, you want the K star, you want the non-zero because you want this to define the torus for you. So you want something that's not zero on the torus and zero outside the torus. Does that make sense? So that is the notion of microlocal merodramy. And what we're going to do in the second lecture is to explain how these functions behave as we start doing Lagrangian these surgeries, and what are the combinatorial rules that allow us to tell so many things about them and why they are so useful. Again, the punchline is, given the set of Lustig cycles, you produce an L compressing system, you take the Poincare dual, that gives you these relative cycles, you compute the merodramies around these relative cycles, which are quantitatively measuring transversality between stern and flux. And those functions are a set of functions, one for each disk in the L compressing system, such that if those functions are different for this weave and that weave, then the tori are different. So now everything can sort of be done till the end and you immediately can tell them apart. Okay? Okay. Questions?
When you go to that new modularized space where you can do more,
Yeah.
you're making some choices on the work time.
Of the base points T.
And then you trivialize the.
Yeah. And so this quotient is literally this comes with a T action. Sorry, this is terrible choice. This set base point is the torus. So this is an affine variety with, like, think about the example yesterday that I worked out in the first lecture. It's like having the X before quotienting. You do remember that it has an action. So those choices translate into the choice of a T action. And then if you want to forget about those choices, you just commute the action. And two different sets of choices will give you, if there's at least one base point per component, will give you conjugate T actions. So they're unique kind of that space. All right, let's take a break.